I'll have office hours today, and I'll have office hours on Wednesday again. So please, if you have any questions about the homework or anything about the class, I'll be available for about an hour after the lecture. So please stop by, and you can even catch me at the end of the lecture. Now that math methods is over, we hope we can now have your exam. Homework 2 office hours by Felipe on 3 to 5 p.m. on Wednesday, rather than having it too late. So we can catch Felipe. So these are the 3 office hours. If you have any questions about homework 2, again, if you have not started, please make sure you start as soon as possible. It's a long homework, so I don't want to be doing it on the last day. So these will be the 3 office hours for the homework. But if you have any additional questions, feel free to reach us via email, and we'll be happy to respond to any questions. All right. Again, quick announcement, that reminder that we have an exam next week in class. So it won't be, it will be during the class time. The only difference is I'll request you that you come 10 minutes early, so 11:55, and then have the class exam will start at 12. Okay. And I'm just doing this to make sure you have enough time. Like, exam is not going to be too long, but just to make sure you have enough time. And from what I understand, most students have conflicts at this time, like class conflicts, so 10 minutes, hopefully you can come. And 12 you will start, and 1:20 p.m. will finish. Okay, so that'll be in the usual class time. So what to expect during the class is the syllabus is lectures 1 to 9. So whatever we'll cover until Wednesday would be covered. Just give me 1 second. Yeah, so lectures 1 to 9. That is what will will be covered in the exam. So the makeup of the exam will be 50% conceptual question, and then there will be a 50% long question, which will be more like a traditional longer problem. So more like a homework problem is 50%, and the kind of questions we ask in class, those will be 50%. And I will upload all the material class questions and everything on Canvas. Okay, so that's what to expect. Almost like a similar structured exam will be posted for you to see on Thursday morning as soon as you submit your homework. You have the exam and you can practice it and post solutions. And I think I'll likely post the exam from last year. That will be the most closest to what you can expect. For the exam, feel free to bring any books, notes, laptops, whatever you want. The only thing we will just ask you is not to consult the web. I mean, you'll not find anything, but just just in general, it's good practice to not search web. You can look at Canvas and books and whatever, but just don't start to Google search and stuff like that. That's all. Okay. So any questions for exam? And next lecture, last 30 minutes, I'll do like a review of the entire material we have covered, and then I'll have an additional online review session, just because the exam is on Monday, so it will likely happen on like a Sunday. But I will post about that. I just haven't figured out all my schedule yet, but I will let everyone know that I'll be just online. Just log in if you have any questions. And of course, if you don't want to if you just want to ask questions over email, that's also fine. Okay. So we'll post more information about the review. I haven't done that. But any questions for the exam or homework? Anything that comes to mind? Yes. Yes, so we are just booking the room, so we'll send out an email. Yeah, we haven't done that yet. So yeah, we'll do that soon. Any other questions? Yes. Oh no, it's just for a practice. It's like this is just, and I think I will have to check, but we'll probably post some additional questions. I mean, there will be some questions in the practice exam, but I may post a few like just conceptual questions if you're looking. So the conceptual questions, by the way, just you see in the practice exam, they are not supposed to be lengthy calculations. They're just conceptual, but there will be some calculations. It won't be like just a minute, and you can answer them. Like a few minutes, you have to think about it. You do like a couple of small steps of math, but it won't be like a detailed calculation. And the idea is to again not test somebody on like their extreme math skills. The question is whether you understand that concept, or if given with the problem, can you apply the concepts you have discussed in class to solve the question? Okay. And you will have similar, I would say, the more difficult side of conceptual questions in the class is very representative of what you can expect in this class. Anything else about exam? Yes.
Sorry, the office hour today.
Oh, I'll just after the lecture for 1 hour. Yeah, I will be available for 1 hour after the lecture. All good? All right. Okay. So let's continue. So just to kind of remind where we are. And I always like to do this as we start to go towards end of a part, particular portion, and we'll end this part one of the class on Wednesday. So where we started. So we started with chapter 1 and 2 of B, where we learned about what are fluxes, Fourier's law, fixed diffusion law, and so on. And then we derived conservation equations and boundary conditions. Okay, so this was the first step. This is chapter 1 and 2 of B. And remember that this is what we basically did. Most of it, this is what you did in your homework 1. Okay, so this was your homework 1. Was these chapter 1 and 2 of D. Okay, so this is kind of introducing. Here, I would say one of the most critical concepts is learning about this molar velocity, mass average velocity difference, how to handle gas phase diffusion, and then also learning about the interfacial balance. I would say that is also one of the key things that most of you may not have seen in your undergrad courses explicitly. All right. Then we moved on to chapter 3, which was simplest form of solving a conservation equation and a boundary condition. That was a 1D steady problem. So in 1D steady, we learned about how to handle just a constant row pseudo binary system, and then we also did a gas phase diffusion problem, the surface reaction. Then we slightly increase the complexity, thinking about 1D supplement, 1D approximately steady systems. And this is what your homework 2 problem 1 is. Okay, so homework 2 problem 1 is a combination of 1D steady and 1D approximately steady. And again, we have supplementary videos for you to kind of walk through those systems. Then we have a 1D unsteady to 1D steady system, which is homework 2 problem 2. And I also created recently just a supplementary video on the liquid evaporation and more mass average velocity and molar average velocity. So this is the first 2 problems for homework, chapter 3. We try to go into these details of slightly increasing the complexity of the 1D steady equations. Then last lecture we started talking. Last 2 lectures we started talking about more complex systems, which is chapter 4 of Dean, and where we are thinking about 2 different kinds of methods. One is semi-infinite geometry and early times. It's the same thing. Those were the similarity transform systems, where essentially we changed a CA of x comma t. Again, its concentration is just representative. It can be temperature with like a theta of eta, where theta is the ratio of concentration to the maximum concentration, or kind of rescaling the y-axis, and then rescaling the x-axis by dividing by the boundary layer thickness. And again, we have another supplementary video trying to answer the questions. You may have a more complex problem, and homework 2 problem 3 deals with this concept. So again, just trying to show you the structure of the course. And finally, we discussed the perturbation in the last class, where we expanded something in small parameter and we basically linearize the problems, and that's homework 2 problems. All right. So this is what we have been kind of questions on the structure till now. I hope everybody can see how the course is flowing. Okay. And now today what we will do is the final part for the for part 1, which is chapter 5 of Dean. Chapter 5 of Dean, and this is finite Fourier transform. Okay, so this is a technique that we will learn. This will remind you of separation of variables that you might have done in your math methods, but it's much sort of, I would say, more simplified form and fewer steps. Okay, so you start with an answer in fewer steps. And very crucially, I want to kind of show you how to think about this different method. So when you see a semi-infinite, early times, think of similarity. When you see a small parameter, think of perturbation. And when do we think about finite Fourier transform? So you want to solve them when you see something which is a linear problem. So that's very important. It has to be a linear problem. So you cannot have any powers of like a second order reaction or a CA del CA by del X. Remember, it has to be a linear problem. And so that's the first requirement. And you would also want to have boundary surfaces. Okay, so boundary surfaces means something like X is equal to 0, Y is equal to L, radial coordinate is equal to capital R, and so on. Okay, so something that's defined. You can, the book actually goes and discusses that you can do this for non-boundary surfaces, but the system becomes a lot more complex. So let's just think of it. We focus on this when we do have boundary surfaces and a linear problem. And why is it necessary to have a linear problem? Is that we'll discuss this in the next lecture in more detail, but so that we can use principle of superposition. Okay, so linear problems have this very nice property that you can actually superpose results without any loss of generality. and we will discuss slightly about this at the end of this lecture and then in more detail when we discuss the and go into the next lecture. Okay, so that's the advantage of linear problems. In general, on a personal level, I can tell you FFT something. This was something I had not read in my undergrad, and I read about this only in my transport phenomena course, and I have actually used it for my research, and I found it to be very helpful. Sometimes it's not only FFT. Sometimes there's a combination of perturbation that reduces the problem to linear problem, and then you can apply FFT. But it's a very, very handy technique, and you can, very quickly arrive at a result, or at least you can understand what a result would look like, even if you don't make the full calculations. It's just very useful to understand problems from sort of this sort of this approach. Okay, so what I want to do today is really walk you through what goes behind finite Fourier transform, how to apply it, and how to apply it effectively. All right. So we have been discussing different methods to solve every problem. So the first thing we discuss is governing equation, right? So we do governing equation. We do boundary conditions. And then third, we want to solve it, right? So this is the typical process we have. So we do governing equations, boundary conditions, and then we want to solve it. Typically at the solution stage, while not always necessary, it's preferred that you non-dimensionalize, right? So for perturbation, you non-dimensionalize by finding a small parameter. For similarity transform, you non-dimensionalize by finding like the boundary layer thickness and dividing the coordinate. So I will assume, and we will do an example today itself, but let's assume we are at this stage. Okay, so we are at the non-dimensionalized stage, and let's take a model problem in mind, and this is just as an example. So an example, this thing we have non-dimensionalized and arrive at the result del theta by del y is equal to del square theta by del x square, and we have been given that x goes between 0 to L, y goes between 0 to infinity. Okay, and we have been given theta of x is equal to 0 comma y is equal to theta of x comma L comma y is equal to 0. So there are two boundaries in x direction, okay, 0 and L, and we have been given essentially the boundary conditions that it's sort of 0 on both x is equal to 0 and x is equal to L for all y's. Okay, so I'm just writing the two boundary conditions in one line just for compactness, and then we are also given, so note there is one derivative with respect to y, so you just need one condition in y. Okay, so you have two derivatives with respect to x, so you need just to clarify, this is theta of x comma y, theta of x comma y. So you have been given that x comma y equal to 0 or y equal to 0 is equal to 1. Okay. Any questions? Yes. So yeah. Oh, sorry. It's y goes from 0 to infinity. 0 to infinity. Okay. Y goes from 0 to infinity. Right, so you only need one condition of y equal to. So first and foremost, so I mean, this is just an example. Theta can be some ratio of temperatures, concentrations. This is just a mathematical finding non-dimensionalized. You get this. Let's assume that. Okay, and we'll do a problem and then see how you can get similar equations. But let's say you get this. So first thing, notice this is a linear problem. Okay, so first thing we notice is a linear problem. Linear problem. Okay. Linear problem. And the second thing we can see is in the diffusion direction, which is the x direction. In the diffusion direction, we see boundary surfaces. Okay. Boundary surfaces. And so that is our cue that we have an option. So x is equal to 0, x is equal to L. This is essentially our cue that FFT might work. FFT might work. Okay. So can anybody tell me why we are not thinking about similarity? We also see like in the y direction, it seems to be semi-infinite. Shouldn't I try for similarity? Anybody wants to try? Yes.
It's not semi-infinite in both x and y, so you would give the similarity.
Yeah, so good track. So Colin is kind of thinking in the right sort of the right spirit. Is the idea is that when you think of semi-infinite, but generally I would say for most practical purposes, you want to think of semi-infinite in the direction of diffusion. So we discussed this kind of briefly. That when we think of semi-infinite system, it's a direction of diffusion. Here the direction of diffusion is x. There's a second derivative with respect to x, but that direction is actually finite. So we cannot. I mean, how will I think of a system as a semi-infinite when the diffusion is actually in a finite domain? Okay, so remember when we say semi-infinite for similarity, typically for most practical purposes, it is that the second derivative has to be in the semi-infinite direction. Here the second derivative is in the finite direction. Second derivative is with respect to x. Okay, this is with respect to x, and then x is between 0 to L, right? So basically, it cannot be thought of as similarity. Or the other option is, if you want to try, you are welcome to try this approach, and then you will find that you will not be able to reduce the boundary conditions in the appropriate form. So you can always still try it out, but you will find that in some conditions, obviously, the similarity won't work. So that's also perfectly valid sort of suggestion that we want to try similarity, but then you will find some limitations. Any questions? Does it make sense? Okay, so when to look for similarity, and it is possible that you can solve sometimes same problem with both, but you will find that FFT is a lot more general always, because it only needs linear and then boundary surfaces. Okay? Always remember that. Okay, so let's say we have this. So this is a Q for FFT, and the way I think about FFT, and again, this is not something which is in the book, just the way I have sort of tried to appreciate is there are 5 steps. Okay, so there are 5 steps in similarity. Oh, sorry, in FFT. So 5-step approach. So think of it like 3.1, 3.2, and so on. Okay. So the first step, which is within the solution step 3.1, is what we like to do is that we like to create sort of, we want to propose a series. Okay. So you want to propose a series solution. So that's how you want to kind of propose a series solution. And what is typically the structure of that series solution is you want to kind of say it is a multiplication of two functions, one only of y and one only of x. Theta n of y into phi n of x. Okay. So first things first, just to clarify, theta is a function of both x and y. We see that. We have boundary conditions in both x and y. Then we saw it's a linear problem, boundary surfaces, great, that's FFT. First step, we propose the solution. Okay? And again, emphasize, again, remember always this phi n of x, this has to be the diffusion direction. This has to be the diffusion direction. Okay, so when we say phi n, and why am I saying that? Because I will say this diffusion direction or phi n is will follow, this is a proposition, will follow an eigenvalue equation minus lambda n square phi n. Okay, and I should note that for the purpose of this course, we are not doing cylindrical and spherical problems. We are only focusing on Cartesian geometry. And if you're interested, if you come across in the research, it's almost identical structure in cylindrical and spherical coordinates. You can look it up in the book. Just out of the interest of time, we focus on more on how to apply it to one class of problems and look at more general problems, but not when the cylindrical. But they are similar steps, very similar steps. So you will just not see something necessarily like this. You will see different structure for a spherical and a cylindrical. Okay, so just want to clarify that for this lectures, we're focusing on Cartesian geometry, but you can extend this to cylindrical and spherical as well. So we get this equation, and so what's the point? The point is that if I can know my lambda n, okay, so I hope you can see if I can know my lambda n, and I know the in the and I know the boundary conditions, then I can actually solve for phi. If this is true, okay, so this is a proposition, and the basic idea behind this is the background math says that if you have a linear problem, you will be able to do this, right? And the boundary sufficient, you will be able to do this. Then you can solve for phi in essentially without doing any effort. So the only thing that you require to solve is theta. Okay. So before we do that, let's just quickly take a quick poll, just so that you can remember some of your basic solutions of what the solution would look like for this problem. Okay, so if we have a form which has d square phi n by dx square to minus lambda n square by and phi n, what's the solution form to expect? All right, I will just give 45 seconds for this. All right, so maybe I will close it around 1 minute mark. This is something you have to know. If you're not aware, we can quickly explain to you how to see that from the solution. So I'm just waiting for the last 15 seconds or so. I think many of you have responded, but just so check. All right, last 5 seconds. If anybody wants to submit their answers. All right, let's close it out. All right, let's look at the results. Excellent. So most of you have the right idea. It is actually the sum series of sine and cosine. If it was a positive lambda n square, then we have fixed in part. Okay. And the square root constitutes the lambda n square. So that's why the lambda n square doesn't work. It's this lambda n. The square root is required. The right hand side. It's a negative sign. If you are confused, just remember that you can always check, differentiate this. Derivative of sine is cosine, then again derivative of sine is minus sign. Similarly, for cos minus sign and minus sign is cos. The negative sign comes here, but for sinh and cos, there is no sign flip. So it's just always positive. Sinh becomes cos, cos becomes sinh. So when it's a plus lambda n square, you will get a series of sinh and cos. If it's minus lambda n square, it's a sine cosine. Okay, so this is just to refresh your memory. So essentially, you propose a series of this form with theta n comma y times phi n of x. You choose the phi n of x. That's called your for your equation, and the solution will be a sum of sine and cosine. Okay? So I hope you can all remember this, that phi n will be a sum of sines and cosines. Okay, so that's essentially, this has to be true based on this proposition. Okay, all right, great. So what? So if we have that, how do we proceed further? And that's where FFT makes things very easy for you. You don't have to go and solve for the phi n, because if you know your boundary conditions, then the book has table 5.2, and you can just look it up. You will know what the solution should look like. Okay. So table 5.2 comes very handy. By the way, we'll post all these slides. So we will post everything for you. You can have it. So table 5-2 says, well, if my boundary conditions is of the form both the values are 0, then use this expression for basis function of phi n. And I should have mentioned, basically phi n is called the basis function. And the solution basically here, this, as you can see at the bottom, this is the same equation we discussed, right? And the coefficient with x is actually the your lambda n, the eigenvalue. So basically, you get sort of this expression, so you can just look it up, right? So what is one thing that you do notice here? So what is the limitation of this table? You notice something? Yeah. So this basically has all zeros only, right? So if you have something which is non-zero as a boundary condition, then either you have to still kind of say, okay, I'll force this series and make sure I somehow satisfy it, or you make your boundary condition homogeneous by trying to kind of subtract and add and so on. So we'll talk about that later. But if your values are indeed 0, then you can just use this and it will work. Okay? So the second step is basically this: is that you want to, once you have proposed a series, is to find the right phi n. Okay, so find the right phi n. So 3.2 is, let's go here, is find phi n generally from table. Okay, you may have to derive it in some cases. The boundary conditions are not this, del phi by del x or phi. If it's a mixed boundary condition, then you actually have to solve the problem. But in most cases, it's fine to just directly look at the table. Okay, so looking at our boundary conditions, let's look at the boundary conditions here. Second step, I hope it's clear. Let's look at our boundary conditions here. Okay, so what do you think is the first? Do I have the boundary conditions homogeneous, or do I have the boundary conditions also have a non-homogeneous boundary condition for phi n? Anybody wants to look at this? They are homogeneous, and why? But I also see a 1. It's an x, right? Because phi n is only a function of x. So don't forget, sometimes there can be that confusion because it's only a function of x. So we have a homogeneous condition, and our conditions are basically phi is equal to 0 is equal to phi is equal to L. So that's the first case. Okay. So we use that, and L is equal to 1, right? So our x is, or is it L? I think I used probably L. So yeah, x is equal to L. So I'll use case 1 from the table. Okay. And say phi n is equal to root 2 by L, root 2 by L sine n by x pi. Okay, so that's what I get, root 2 by L sine n pi x by L. Okay, so that's how I get the value, which is here. That's my phi. Okay. So that's step 2. So first step, we propose a solution. Then second step, we find a basis function. Okay, so this is, by the way, I should just out of completeness, this phi n is called the basis function. All right, then third step is the definition, modify the governing equation. Okay. So what do I mean by that? So the point is, the first thing is the important part is we had 2 parts of our series, right? One was theta n and one was phi n. Based on the boundary conditions, we know about phi n. That's step 1. But you still have to find theta n, right? And obviously theta n has to depend on governing equation. We haven't used it yet. What we have only used are boundary conditions. So we haven't used the other condition in y or the governing equation. So that's where we use it now. Is that what you modify the governing equation by using the definition of theta n. And we haven't really defined theta n, so that's the definition now is, I mean, and I'm not going into some of the more details of how we define these theta n and phi n, and the book does a very good job of actually explaining the rationale, orthonormality, and all the details behind the series. So this is just out of interest of time, we are not going to cover it. So just accept it at the face value. But if you are just curious, you can look it up. They do go into the detail of how to get there. So the different definition of theta n is it's theta times phi n. So we integrate out the x dependence. So remember that theta n is only a function of y. Okay, so that's our proposition, and this is the property for this set of problems is that if it's theta of x comma y phi n d phi n x of dx, and we go through the entire range, which is boundary surface to boundary surface, 0 to L, and that is my definition of theta. So that's the whole point. That's what you get. So if you have this if you define your theta n like this, remember your governing equation is del theta by del y del square theta by del x square. Okay. So this is what you know. Phi n we know already through boundary conditions in x. Now this is my definition of theta n and this is my governing equation. So what do? I simply just multiply with phi n and integrate, because that's how you can use the definition of theta n, right? So that makes a lot of sense. Is that I know this is the equation in theta, right? But I want to get expressions like this, right? So what you will do is you will take your governing equation. So that's why the idea is modify the governing equation. You basically do phi n dx 0 to L del square theta by del x square phi n x dx 0 to L. Okay. That's what you do. So you basically first step propose a solution, second step identify the basis function, third step you use the definition of theta n to modify a governing equation. Okay, and that's why, because we want to convert from an equation from theta to theta n, because that's the only thing we don't know yet. We already know phi n. So you want to find an equation for theta n that you can solve. And how do you do that? Is by modifying the governing equation by using the definition of theta n, which again I said is not something that you just have to accept it at the face value. That's something that will be kind of is given to you. So you don't have to worry about. If you want to read, you can read about it where you can kind of show that. But essentially, if you have that, you kind of follow through the steps. Okay. Now, because of the properties here on the left hand side, I hope all of you can see is this is essentially d by dy of just interchanging, because phi n is not a function of x, not phi n is not a function of y. I can say, okay, right? I hope you can see that phi n dx. Sometimes my n and x can get confusing. So dx, okay. This are just interchange because phi n is not a function of y, right? So I can simply take the y outside and integrate first to phi n and then take a derivative. And what is this expression? Theta n, right? That's a definition of theta n on top. Okay, so this becomes d theta n by dy. Okay. Now, can I take the derivative of x also outside on the right hand side? Double derivative, like I did in the left hand side. Why or why not? Yeah, I hope you can see that because phi n is dependent on x, right? So I have to, by integrating this, I cannot just take it out here. Phi n was independent of x, that's why I could take the y out. Just remember that, like, in case you are not as used to this. So I can't do that, and the way to do this is to use by parts. Okay, we will not do this. Again, it's a standard solution. And by the way, I have, like I said, I've used FFT many times. I never do this myself. I just look up the result in the book. I mean, it's a standard result, and you can just look it up in the book. You don't have to feel like you have to know the solution itself. Okay? You can just look it up in the book. So what's the result? So the result is, you can essentially say that this becomes, this has two parts. It becomes, and this is 5.4-15 in the book. And the result is del theta by del x times phi n minus theta times d phi n by dx. So this is like an expression, like a term, and it has limits 0 to L minus lambda n square theta n. Okay, so this is kind of, you can just look it up. This is not just, and you can derive this also, apply by parts twice. Apply by parts twice. If we apply by parts twice, you just directly get this result. Okay. So can anybody tell me why did I want to go from this? Anybody suggests why would I want to get the information in this form? For this you don't need a map. Just kind of, so we start from the governing equation, right? So why am I trying to integrate by parts and trying to come up with this sort of expression? Absolutely, right? Because you want to solve for theta n. You already know phi n. So you want to solve for theta n. So you're trying to convert everything in form of theta n. So you get this lambda n square times theta n here, and lambda n is just a coefficient with respect to x. And we'll talk about it. And then this part is what essentially you get at the extra part, which is the boundary term. Okay. Now, basically, the idea is based on the boundary conditions. In most cases, you will know this value. That's the idea. You will know this value in most cases, and so you will at the end of the day just get the differential equation in terms of n. So how do we do that? And don't forget there are two terms, and both the terms have to be evaluated at both L and at 0. Okay. So what is the value of phi n at x is equal to 0? So our phi n is, remember, phi n is root 2 by L root 2 by L sine n pi x by L. What is the value of phi n at x is equal to L? 0, right? Because you just put x is equal to L, it's equal to sine of n pi. So this goes away, right? At x is equal to L. What happens to value of theta at x is equal to L? 0, boundary condition, right? So both terms drop out at x is equal to L. Then you basically get at x is equal to 0 phi n, even at x is equal to 0. You look at the boundary condition, sine of 0 is 0. And we also know theta is 0 at x is equal to 0 in a boundary condition. Right? So all four terms, basically, both the terms at and both x is equal to L and x is equal to 0 drop away. And all you're left with is simply minus lambda n square theta n. Okay, so that's the point. So now you get a differential equation ODE in terms of theta n that you can integrate. A word of caution, most students basically assume that this will always be the case. Please note that this is the general equation for the given governing equation, and you may have a slightly different governing equation, but don't forget the boundary terms. Okay? So always make sure that you are doing the steps systematically and coming up with an ODE. Okay. Now, can I just solve it? Do I need anything else to solve an ODE like this? So what have you not used? Let's go to the problem. Boundary condition in y. Very good. So we have used the governing equation. We have used the boundary conditions in x. What I have not used yet is the boundary condition or the boundary condition in y in this case. And so we have to make sure the step 4 is 3.4 is modify the remaining initial / boundary condition. It can be an initial condition or a boundary condition. You do want to make sure you modify this. So what am I told? I have been told that theta of x comma y equal to 0 is equal to 1. So how will I find theta? How will I convert this into an appropriate boundary condition of theta n? Any thoughts? How will I convert this into an appropriate boundary condition? Is by using the definition of theta n, right? I know theta of n is phi of x comma y, phi n of x comma dx. So what I just basically use the definition. So use definition. So I'll just remind everyone again, just so you're seeing the process. Theta n of y is equal to 0 of L phi n of theta of x comma y phi n of x dx, right? So theta n of 0 naturally then becomes 0 to L theta of x comma 0 phi n of x dx, right? That's it. I've just substituted the definition of theta n. And what is this value? 1. This has been given to us, right? I already know phi n, right? So this becomes 0 to L phi n of x phi n of x dx. And this essentially becomes 0 to L root 2 sine root 2 by L sine n pi x by L dx. And the right hand side is very easily calculated. It's an integral of sine. You get a cost, you substitute the limits, you get a value. Okay, so it is trivial to do that after this point. And finally, 3.5/6 is solve for theta n. Now that you have the equation, then substitute in theta equal to theta n y phi n of x. All right. That's how you finish the problem. It's a long step process, but it looks, so we have gone through all the details, but as you see when you start to do examples, it's actually very fast. Once you know what to do, propose a solution, look at the basis function, modify the governing equation in theta n, and modify the initial boundary condition in theta n, and then finally solve and substitute that. and this will work as long as the problem is linear and the problem has the linear and the boundary. Any questions on this process? Yes. So yeah, great question. So the next question is, what happens to system if I have diffusion in both x and y? So this is problem. If you look at a homework problem, it has diffusions in both the directions. So how do I work with it? Any thoughts? Any ideas? So you can choose basic function in either direction. Doesn't matter. You can choose phi of x or phi of y. You follow the same process. You can just that you have more flexibility and you can choose basic function, and you have to get the same answer. So I have to recall. I think the problem does not ask you to do both at the same time, but it does ask you to plot a few things. But you can actually make sure you want to do the steps. You can do both steps. You have to get the same answer, and it has to work out because so it depends. If it's only one direction in diffusion, you have to choose it for basis function. But if both directions are the same diffusion, you can choose either. Doesn't matter. Any other questions? All right, so we are, yes, please.
If you just use separation variables, you get the same thing.
You get the same result. Yeah. So the only advantage of the book has a lot of details about why is this preferred is that once you kind of get the hang of how to use FFT, it is just much faster to kind of do, because you just know then in separation of variables you have to solve both the equations all the time. So in this case, it just makes it more systematically laid out. But there are a lot of similarities in both the methods. In fact, they have similar ideas. Clearly, we are separating the solution in x and y. Just that it's a little bit more intuitive and fewer steps. So there is nothing against separation of variables. It's just a little bit more easier to do it. It's the same, but it's the same solution.
What is it?
Oh, the boundary surface. So the boundary surface you cannot. So if my good question. So what if I had what would happen if I had, let's go here, if I didn't have x is equal to 0 to L, if I had x is equal to infinity, everything will break down, right? Because if you look at it here, I cannot use the basis function anymore. So you need to have some sort of finite domain in which you solve it. You cannot solve it in a purely infinite system. You will not be able to use this function. Good question. There is one domain that has to be finite, which is x is equal to 0 and L in this case. If x was going to infinity, you will not do so. Any other questions? All right, so I think let's take a break till and just come back at 12:53, so 5 minutes, and then we'll do an example and then discuss more. I can take the questions over there. Yeah, I can ask. Two more meetings.
There is so much So text, where that's, what do you do in your lab? Yeah.
All right, let's begin. All right, let's begin. So let's take an example to like kind of apply FFT, and then we'll discuss a little bit about linear principle of linear superposition. Is that you have a system which is a finite going from x is equal to 0 to x is equal to L. It's like a liquid phase system where some gas is dissolved. Think about it like that. And then you have two boundaries where the concentration is 0. Okay. So think of it like you have saturated a gas, a liquid column with a gas, and then the boundaries don't have any gas. Okay. So the boundaries cannot have any concentration. So with time, essentially the system will start to kind of the gas will start to leave the system. And this is we have to find the CA of goal is to find CA of x comma t. Okay, so that's the idea. Pseudo binary constant rho, and I should mention that no convection, so it's just a stationary liquid phase. So there is no convection or something like that. This is what we want to solve. So the idea is we want to kind of show the application of FFT, but I wanted to kind of formulate the problem from scratch. Okay, so this is the problem. How do you start? You start with governing equations. Governing equation. So we have del CA by del T, pseudo binary constant density. So you can use this equation. This RA. So don't forget this equation. We do have an steady system, so this will stay, but no convection, so this goes away, and no reaction, so this goes away, right? So hopefully this is becoming easy to see now. You know, we've seen this several times, and it becomes del square CA by del x square. Del CA by del T is equal to dA del square CA by del T. These are the equation. The step one, unsteady diffusion, you get this. Second step is boundary conditions.
boundary conditions. I hope you can see it's constant value at both ends. Just give one value. There is no flux condition and anything like that. 0, and initial condition is IC is CA of 0 comma, sorry, x comma 0 is C naught. C naught. Okay. So simple, like to find the governing equation, you have the two boundary conditions, you have the initial condition, and so on. Any questions on this? Anything that is confusing, but I hope like if you are give you a problem like this, you can first do these governing equations and boundary conditions. So we have this problem. Now we want to solve it. So anybody wants to solve it using similarity, why and why not? So when you want to solve it, why can't we solve it using similarity, or if you want, any thoughts on that? Yes. Great. It's not in the direction of diffusion. Diffusion goes from 0 to x. Okay? So in some cases you can solve it in early times, but we clearly know this is not the problem is asking us to find a linear solution. So we will just not use similarity because it's finite domain in x or the direction of diffusion. Okay. We are not looking forward to any sort of like perturbation method either, because there is no clear obvious solve small parameter. Right? If there was a small parameter, you might want to try it, but there is clearly nothing like that. But we do know the problem is linear. The equations are linear and our surfaces are boundary surfaces. Okay. So that we can clearly see. And so that means this is a good problem to solve using FFT. I hope that can make sense. A good problem to solve using FFT. All right, so we will non-dimensionalize this now. First step is generally to non-dimensionalize. And I apologize, I have to go a little bit. I'll just give you the, you can try to, do this at home just to become comfortable, but you just basically define CA by CA naught. You define tilde of x by L. Typically, you want to go from 0 to 1 for both concentration and x. And then you will, once you do that, you will see that time comes out to be dAt by L square. And if you do that, you essentially get del theta by del tau is del square theta by del x tilde square. Okay. So once you do this, you will drop out this any coefficients, and we know the initial condition is 1 and the boundary conditions are 0. Any questions there? Yes. Handwriting is not as good. It's DAT. Absolutely right. This is DAT by L square. Okay. So please don't hesitate to let me know if anything is confusing. I realize a lot of symbols floating around. Anything is unclear, do ask. Any questions on the governing equation, boundary condition, initial condition? So you get this. Now it's a linear problem, boundary surfaces. We want to try FFT. So let's go to 3.1. Propose a series. Okay. So step 1. So what kind of series do we want to propose? Do we want to say theta is theta n of x phi n of tau, or do we want to say theta n of tau phi n of x? We have these two options. Anybody wants to say which one? So x tilde, yeah. Anybody wants to say this form? Second one, right? Because phi n is always the direction of diffusion. Okay, so don't forget that basis function is always the direction of diffusion. So I can't use this. Diffusion direction always goes behind the basis function. Diffusion direction. Okay. 3.2, identify basis function. So what are my basis function? I have to identify. And for that, we go to table, right? So propose a series, we propose a series, then now we want to go towards table. Let's look at the table now. So we have this table back. So what should be the case for? Case 1, 2, 3, 4, which case? Anybody? First case, right? Because boundary condition in both x is equal to 0 and x is equal to 1, or x is equal to 1 is 0, right? It's given. So case one. All right, I just wanted to emphasize one thing that Paul mentioned. What is this phi not equal to? That's actually with case four. Okay, so this with case four has two parts. One is a constant part and then one is a series part. Okay, so this is to phi naught plus phi n. Okay, so don't worry about it. It's just a small detail. Like no problem is why I require. This is a small detail. So the last column will go to case two. Okay? But for this column, we will do case one. Okay, because the boundary conditions are constant and both sides value is constant. So let's go back. It's case one. Okay. And what is the value of L is equal to 1, right? Because our full domain x tilde goes from 0 to 1. Right? So phi will become root 2 sine n pi x tilde. Okay. Any questions on phi n basis function? And just so that you get used to this, remember that the coefficient of x in the sign becomes your lambda n. And if you're confused, why did I write it like that? Remember the solution we discussed. I'll just come back to this screen. But remember that our phi n is the form lambda n times x. Okay. So whatever is the coefficient within the sign with respect to x is your lambda n. It's just that's it. Okay. So lambda n is n pi. Yes, please. Yeah. Oh yeah, sure. Yeah, good question. So what I'm saying is, note that I'm solving the formula in x tilde domain, right? And x tilde goes from 0 to 1. Okay. And the table basically, table here basically wants you for going from x tilde going from 0 to 1. So remember, we are solving the x tilde domain, okay? 0 to 1. X tilde goes from 0 to 1, and so I put L equal to 1. Make sense? Any questions here? I hope it's clear. That's why it's, L goes away, it's just 0 to 1. All right. Yes, please.
Could you go back to the-
Sure. Yeah.
So the third application instead of 1 or L.
That's 1. Yeah, that's 1. Yeah. So it's 1. This is x tilde equal to 1. Any other questions? All right, good. Okay, so we got the basis function. We've proposed a series. Then the third step is to modify the governing equation, right? Modify governing equation. So we'll start with del theta by del tau is equal to del square theta by del x tilde square, right? And we have to remember that we have to make use of the definition of theta n, which is theta times phi n. But I just want to emphasize again, in case somebody missed it, that your integration domain from x tilde will be 0 to 1. L is 1 here. So x tilde goes from 0 to 1. So definition of theta is like that. So I will take integrate. So I'll integrate using the definition. Integrate. So you will get, you want to basically, there's theta this will look a little bit of repetition, but I hope just adding clarity now, because we are just trying to follow the process. Okay, so I've just used the definition now. Sorry, this is a little, go up. I'll remove the cursor from here. So I have this basically integrated by using the definition phi n x dx, phi n x dx. Both sides, like we discussed, because phi n is not a function of tau, this will simply become d theta n by d tau, right? And remember that the formula here wants us to kind of use, I'm using the by parts, and like I'm skipping the steps by using a 5.4-15 del theta by del x times phi n minus theta times del d phi n by dx. I'm just saying some will come from definition of theta, some will come from definition of phi, some terms 0 to 1, and minus lambda n square theta n. So this value, and I want to emphasize, we know this lambda n is n pi. Okay? So I will write it again. So we get the same term. Okay? Now I don't want to go to the detail again, but as you can imagine, because the values are given to be 0 and both 0 and 1, if I substitute the homogeneous boundary conditions, so all of this will just go away. Okay, remember, theta n is sine of n by x. We substitute x tilde equal to 1, this goes away. Theta is 0 and x equal to 1. Similarly for 0, again, both the values go. Okay, so if you're not comfortable, don't worry, just take a few minutes at home and try to substitute the value, and you'll convince yourself that all of these values just simply go away because of homogeneous boundary conditions. And all you're left with is d theta n by d tau is equal to minus n pi square times theta n. This is what it is. So very simple, you can equation for theta n after we have substituted the boundary conditions using phi n and theta, and we have modified the governing equation. Okay. So steps again, we propose a solution, basis function, and modify the governing equation. Okay. Then finally, 3.4 is modify the initial condition. Modify, in this case, it's time, so I will say initial condition. And remember that I had theta of x tilde comma 0 was 1. So my theta n of 0 would be theta of x tilde comma 0 phi n dx 0 to 1. And this is because this value is equal to 1, it becomes phi n dx 0 to 1. And this is equal to root 2 sine of n pi x tilde theta n of 0. Right. I hope you can follow this. Any questions? I know I'm with math and skipping a few steps, but hopefully you can all see the structure, even if a couple of steps are a little unclear or you haven't been able to completely see the math, but I hope the steps are clear. Any questions on theta n of 0? How did we do this? We use the definition of theta n. Just we substituted y equal to 0 and because tau equal to 0, and because we knew the value of tau equal to 0 or the initial condition, I could simply get phi n. And phi n you already know, root 2 sine n. So what is it? That is integral of sine and sine of x? Minus cos, right? So we'll just say this becomes minus cos by n pi. So minus root 2 by n pi cos of n pi x tilde going from 0 to 1. And if you evaluate this value, it comes out to be root 2 into 1 minus 1 raised to the power of n by n pi. Okay. This is what the value of theta n comes out to be for each value of n. Just want to make sure my steps are correct. This is fine. So last step, we're just almost there. 3.5 is to solve for theta n and then substitute finally. Again, this is not that complex if you just integrate this. So I'll shade this out, this, and use this with this value. Okay, so plus this, use this as an initial condition or the condition to integrate d theta n by d tau. And what you will get out is pretty simple. You will get theta n is equal to root 2 of 1 minus 1 raised to the power of n by n pi exponential of minus n pi square tau. Okay. Finally, the solution becomes theta n phi n dx tilde, sorry, no dx tilde, just phi n, and this becomes, because there's a square root 2 here in theta n and there's a square root 2 in phi n, this will become 2 times 1 minus 1 raised to the power of n by n pi exponential of minus n pi squared times tau sine of n pi x tilde, and goes from 1 to infinity. So this is the full solution for theta n as a function of x comma tau, and it is able to. So hopefully you can see all the 5 steps in process. First, propose a solution. Second, basis function. Third, modify the initial governing equation. Fourth, modify the initial condition of boundary condition. Fifth, solve for theta n and substitute to get to the answer. Any questions here? So what Saradeep is asking is, okay, so what if you have, okay, so you can do this, but you do rely on this table. What if the boundary conditions are not known, right? So you do know the general solution here, right? So then you will have to come to this general solution and find A1 and B1. So it's possible. It just takes a little bit of work, but you can find it. It's like for mixed boundary conditions, for instance, it's known, like, you know, you get like a B8 number or something, and it becomes like you get an equation for lambda n at the end, which you can use to solve. Any other questions here? Yes. Correct. Yeah. So absolutely. So we're trying to kind of separate the contribution from x, which is a boundary condition, and then theta is the condition. So you're trying to convert, technically, you're trying to convert completely to a ODE. By basically removing the x dependence, I use phi n, and then getting the ODE. Any other questions here? All right. Okay, so just out of, I mean, it's always good to check this, and not a bad idea. I also learned, like whenever I look at the expressions, I will always try to check this. So you have this, if you put x is equal to 0 here, you get a sign of 0, like for all your terms, right? The sign of 0 is 0, to satisfying the boundary condition. If you put x is equal to 1, you get again sign of n pi. So for all your n's, sign of n pi is 0. So you again satisfy the boundary condition. And now when you put tau equal to 0, what you get for, so just to kind of check, like, and check boundary conditions are satisfied. Boundary conditions are satisfied. Okay, so you can check that. But if your initial condition, you basically get theta of x tilde comma 0. So this is all one term. I'm just writing it like this, right? You get this term. So how can I check this is equal to 1? We want this to be 1, right? This is our initial condition. So remember, you plotted something in your homework, in the first homework. You were trying to plot some sort of a series, and that gave you an answer to be 0, I believe. So that's how basically you plot this. Now in the same focus, changing the expressions, you will get 1. Okay. This series, again, this is the whole point of Fourier series, because this will converge to a solution. As it's kind of gives you the. Oh no, you have to sum for enough terms to get there. Before for all x's, but for each x it has an infinite sum. Right? So you will basically like the way you plot it, you keep summing till the value stops changing or becomes very close to one more change, and then you can see this will come out. So if you're curious, you can just plot this. And if you did the math correctly, you should get it. Otherwise, you will just give the wrong answer. Okay. And if you are really curious, you can also try to differentiate this with respect to time and with respect to x, and you will see you'll get back the initial the governing equation as well. Okay, so that is also another check. All right. So hopefully this was helpful. Last 5 minutes, I just want to discuss some ideas of superposition. So let's just do one quick question, and so. Sorry. Let's do just one quick poll question, and then I'll discuss principle of linear superposition. So let's imagine you have something like this, okay? And you don't have to use any math for this. I just want you to see this.
you get the same problem, kind of a similar problem you were doing, but now I add a reaction. Okay? So now you have added a reaction to your system. What do you think will change? Do you think the equations for theta n will change, or do you think the basis function? Okay? Think about it, look at the equations, look at the boundary conditions, initial conditions, and then we'll just put in your answer. I'll give another 45 seconds or so, and then we'll close this question. All right, last maybe 10 seconds or so. Get your answers in. All right, let's close it out now. All right, so let's look at the results. So there's some split. Some students say it's basis functions. Some say it's theta n, more biased towards theta n. Anybody wants to kind of volunteer and give why you think it's clearly? Absolutely. So absolute Tim is right that you have the boundaries to be the same, right? X equal to 0. The boundary conditions are the same. And your boundary conditions determine your basis function. That remains the same, and that's why theta n changes. Okay. And if you do the problem, it's really nice. If you do this problem, I dig into it, try it at home. It's identical, almost like it's a full different problem. Just get a damn polar number extra, and it becomes like a part of a differential equation. You get a very similar looking answer, but it also has no reaction. Okay, so please do try this. Again, it's a good practice, I would say, for your clarity of how to solve this. And you will get, do try it at home. Right? So the answer is B, because you're basically, the governing equation has changed, not a boundary condition. And governing equation becomes a part of theta n, and boundary conditions are a part of phi n. Okay. Now, last question I want to kind of emphasize is this is your homework problem actually. So you will do this in your homework. The point is how to choose basis function for non-homogeneous boundary conditions. Okay, so this was something that came up last year, and I did this at home last year. So how do you choose basis function for non-homogeneous boundary condition? This is your problem, and the problem, there are two processes. Okay, so one option is for you. So you can see first, this is Saradeep had asked a question, how do I choose both basis function? There is now diffusion in both x and y. So if you look at the boundary condition here, governing equation here, it's del square by del x square and del square by del y square. So both x and y. So you can choose either. Okay, so we'll ask you to choose one. And then there are two basis options. One is you will force a solution and say, well, I'll assume it to be as if it was 0. Okay, and choose the same basis function, and I'll try to satisfy the equation. And that's what basically the problem tries to do in your homework 2005. But you can also make the boundary condition homogeneous by substitution. Okay, so what you do is essentially you kind of create a dummy variable which is able to make the solution boundary condition 0. And I hope you can see that when you have boundary conditions C and naught everywhere, if you just subtract C and naught, C minus C and naught will have the boundary condition 0 everywhere, right? So that's one way to make the boundary condition homogeneous, and then you solve for C minus C and naught instead of solving for C, because that's easy. Okay, so the homework problem will make you do this top part, but you can also do this and get to the same answer. And you can look at the difference. There are differences in the solution, right? There is a lambda n there, and there is a -1 there, and there's something at the front here which there is no +1 there. And if you do it, and actually you can do this in yourself, you do find that the solutions are identical. However, if you look, method 2, which is the one with sort of method 2, has a slightly better convergence at the end point, and you can see there's some fluctuations at the right hand side at the ends. So it is always preferred, if you can substitute, you should substitute. Okay, and make the problem homogeneous if it's possible. If it's not possible, then of course you have to stick to the particular solution, and you get a slowly converging solution. And to that end, I will just make one last point. We have uploaded a supplementary video which goes into substitution in a little bit more detail.
and I'll just leave it here. So what it does is it tries to homogenize using a steady state solution. Homogenize using steady state, okay? Using steady state. It's a 25-minute video, so it's a little bit long, but it walks you through every single step, slowly trying to show you what's the logic of going from the solution you would think, and then try to homogenize using steady state and add two solutions, and you will get the correct answer. Okay, and we'll discuss this more in the next class. Okay? So hope this was good. So I'll have office hours now, and then we'll meet on Wednesday to have more discussion. Thank you.